uh, okay, so now let's take a look at double integrals over type 2 regions. So in a type 2 region, the top boundary and a bottom boundary are straight lines like this. However, the left boundary and the right boundary are allowed to be curves. And so to describe a type 2 region, the y variable varies between two constants, say here C and D. However, the x variable varies between two functions. So here there's a mistake in this should be with respect to y, right? Because here x is varying between two functions of y. So this should be a y, and this should be a y. Okay, so so for a type 2 region, because y is the one varying between two constants, the inner integral has to be integrated with respect to x first, and then we integrate with respect to y. So the double integral has to be set up in this way. So one thing to be careful about is that some regions can be considered both a type 1 and a type 2 region, and some integrals are more easily calculated one way versus the other. So in some cases, we might have to switch integration between a type 1 and a type 2 region. However, the setup is slightly different between a type 1 and a type 2 region, right? So if you need to switch the order of integration, you have to also be careful about how you describe the region R and setting up the limits of integration properly for a type 1 or a type 2 region. So with that in mind, let's take a look at an example. Here we have this region R that's being described as the boundary of the graphs y equals square root of x. So y equals square root of x is this curve here, and x equals 0 is this boundary on the left here, and then y equals 1 is this boundary at the top here. Okay, so in this example, this region can be described as a type 1 region or a type 2 region. So let's describe it in each way, right? So if you remember, in a type 1 region, the x variable varies between two constants. So here we have to describe x as being between two numbers, right? So x goes between here and here, right? So the left boundary is when x equals 0, and the right end of the region stops here where x is equal to 1. So x goes between 0 and 1, and y, so y should vary between the bottom and the top, right? So what's the bottom boundary is this curve here given by the square root of x, and the top boundary is where y equals 1. Okay, so that's being described as a type 1 region. How about as a type 2 region? So in a type 2 region, y is between two constants, right? So at the bottom, this is where y equals 0, and at the top, it stops at y equals 1. So that's the boundaries for y. And what about for x? Right, so x goes between left and right. So when we describe the region, we should think of the left boundary and the right boundary. So on the left, I have the boundary here, where x is equal to 0. And on the right, so you have to be careful here, right? Because this x equals 0 is the entire vertical line boundary. However, when we go to the right here, it stops at this curve here, right? So which is described as the square root of x. And so when we describe the right boundary, so we can't write the square root of x, right? Because here it should be some function of y. So what we need to do is to rewrite this as x in terms of y. So x is equal to y squared, right? Just square both sides. So we can describe as x equals y squared. And so the right boundary is y squared. So this is how you describe the region as both a type 1 and a type 2 region. And notice, even though it's the same region, the description is slightly different in each case. Okay, so if we go back to this integral that we're trying to calculate, right? So you notice that this is described as here x is going between 0 and 1, and y is going between the square root of x and 1. So this setup here is as a type 1 integral, right? So this is a type 1 region. However, this is actually not possible to calculate by hand as a type 1 integral, right? So what we do is we switch to a type integral. Right, so here when we switch to a type 2, we have to change the limits of integration according to how it's described as a type 2 integral. Right, so y is on the outside, y goes between 0 and 1, x is on the inside, x goes between 0 and y squared. The function stays the same, so 3 over 4 plus y cubed. And then I switch the order of integration, so dx goes first and then dy. Okay, so when you set up an integral like this, make sure everything makes sense, right? So the inner integral is with respect to x, and in the limits of integration, it doesn't contain any x, so that's okay. And the outer limits of integration is only numbers, so that's also okay. Okay, so everything seems to be set up properly here, and now we're ready to calculate. Okay, so what is the antiderivative? So here we're integrating with respect to x. This doesn't contain any x at all, so it's just one big constant. And so the antiderivative of a constant is a constant times x. Right, so you get 3x over 4 plus y cubed, evaluated from 0 to y squared. The outer integral still stays the same. Okay, so now we're plugging this in for x. So what do I get? The integral from 0 to 1. You get 3y squared over 4 plus y cubed. And then minus, if you plug in 0, it's just 0. So that doesn't do anything. Okay, so this is what we get. And okay, so now here we have to use a u substitution, right? So the idea here is that in the original integral, trying to integrate this with respect to y is hard, but by switching the limits of the integration, we were able to get this antiderivative fairly easy, because this whole thing is just a constant with respect to x. And by doing it that way, now we're allowed to do u substitution here. So u is equal to 4 plus y cubed du is equal to 3y squared dy. Right, so notice how this 3y squared pops up here, so that's going to simplify things by a lot. So we integrate. The limits of integration are with respect to y, so let's make a note of that. Y goes from 0 to 1. Again, the 3y squared and the dy changes to du. And the 4 plus y cubed becomes u. So it's just 1 over u. Okay, so the antiderivative of 1 over u is just the natural log. Well, let's plug u back in, right? Because here this is in terms of y. So what was u? 4 plus y cubed. Evaluated from 0 to 1. Okay, so if I plug in 1, I get the natural log of 5 minus, if I plug in 0, I get the natural log of 4. And then now this just needs to be calculated. So I calculated this beforehand, and it comes out to be 0.2231. Okay, so we have an example where we were presented with a type 1 integral. However, to proceed with calculating the integral, we need to switch to a type 2 integral. But again, when you switch the order of integration, make sure you first describe the region properly so that you know how to set up the limits of integration, and then you can calculate it from there.